Yes, welcome back. I'm eating a little bit candy. Let's finish this important PDF. Semiconductor device fabrication. I will add this to my read again list. This is 11:30. But I have to get up my bed soon again. I'm uploading 3 videos. My back is hurting a little bit. It's like 28-degree hot. Yes, let's read this finish so I can upload this and get to bed. This is my 10 years old Canon. This is my 10 years old Canon camcorder. Yes, I'm eating a little bit candy, so I make a little noise. Sorry for that. I have to check my cell phone. And alarm clock is on. So let's finish this and continue tomorrow.
Front end of line, field processing. Field processing refers to the formation of the transistors directly in the silicon. The raw wafer is engineered by the growth of an ultra-pure, virtually defect-free silicon layer through epitaxy. In the most advanced logic devices, prior to the silicon epitaxy step, tricks are performed to improve the performance of the transistors to be built. One method involves introducing a straining step wherein a silicon variant such as silicon germanium, SiGe, is deposited. Once the epitaxial silicon is deposited, the crystal lattice becomes stretched somewhat, resulting in improved electronic mobility. Another method, called silicon-on insulator technology, involves the insertion of an insulating layer between the raw silicon wafer and the thin layer of subsequent silicon epitaxy. This method results in the creation of transistors with reduced parasitic effects. Gate oxide and implants. Front-end surface engineering is followed by growth of the gate dielectric, traditionally silicon dioxide, patterning of the gate, patterning of the source and drain regions, and subsequent implantation or diffusion of dopants to obtain the desired complementary electrical properties. In dynamic random access memory, DRAM, devices, storage capacitors are also fabricated at this time, typically stacked above the excess transistor. The now defunct DRAM manufacturer Chemunda implemented these capacitors with trenches etched deep into the silicon surface. Back end of line, bill, processing. Metal layers. Once the various semiconductor devices have been created, they must be interconnected to form the desired electrical circuits. This occurs in a series of wafer processing steps collectively referred to as bill, not to be confused with back end of chip fabrication, which refers to the packaging and testing stages. BEO processing involves creating metal interconnecting wires that are isolated by dielectric layers. The insulating material has traditionally been a form of SiO2 or a silicate glass, but recently new low dielectric constant materials are being used, such as silicon oxycarbide, typically providing dielectric constants around 2.7. compared to 3.824 SiO2, although materials with constants as low as 2.2 are being offered to chip makers. High dielectrics may instead be used. Interconnect. synthetic detail of a standard cell through 4 layers of planarized copper interconnect, down to the polysilicon, pink, wells, grayish, and substrate, green. Historically, the metal wires have been composed of aluminum. In this approach to layering, often called subtractive aluminum, blanket films of aluminum are deposited first patterned, and then etched, leaving isolated wires. Dielectric material is then deposited over the exposed wires. The various metal layers are interconnected by etching holes, called vias, in the insulating material and then depositing tungsten in them with a CV technique using tungsten hexafluoride. This approach is still used in the fabrication of many memory chips such as dynamic random access memory, DRAM, because the number of interconnect levels is small, currently no more than 4. More recently, as the number of interconnect ovals for logic has substantially increased due to the large number of transistors that are now interconnected in a modern microprocessor, the timing delay in the wiring has become so significant as to prompt a change in wiring material, from aluminum to copper interconnect layer, and a change in dielectric material, from silicon dioxides to newer low-K insulators. This performance enhancement also comes at a reduced cost via Damascene processing, which eliminates processing steps. As the number of interconnect levels increases, planarization of the previous layers is required to ensure a flat surface prior to subsequent lithography. Without it, the levels would become increasingly crooked, extending outside the depth of focus of available lithography, and thus interfering with the ability to pattern. CMP, chemical mechanical planarization, is the primary processing method to achieve such planarization, although dry HVAC is still sometimes employed when the number of interconnect levels is no more than 3. Copper interconnects use an electrically conductive barrier layer to prevent the copper from diffusing into poisoning its surroundings. Wafer test. The highly serialized
Yes. I need to put 3 videos public. It's 11:40 p.m. It's midnight, so they have to be for today. Yes, the last one is not ready. It's on 95%.
nature of wafer processing has increased the demand for metrology in between the various processing steps. For example, thin film metrology based on ellipsometry or reflectometry is used to tightly control the thickness of gate oxide, as well as the thickness, refractive index, and extinction coefficient of photoresist and other coatings. 39. Wafer test metrology equipment is used to verify that wafers haven't been damaged by previous processing steps up until testing. If too many dies on one wafer have failed, the entire wafer is scrapped to avoid the costs of further processing. Virtual metrology has been used to predict wafer properties based on statistical methods without performing the physical measurement itself. 1. Device test. Once the front-end process has been completed, the semiconductor devices or chips are subjected to a variety of electrical tests to determine if they function properly. The percent of devices on the wafer found to perform properly is referred to as the yield. Manufacturers are typically secretive about their yields. but it can be as low as 30%, meaning that only 30% of the chips on the wafer work as intended. Process variation is one among many reasons for low yield. Testing is carried out to prevent chips from being assembled into relatively expensive packages. The yield is often but not necessarily related to device, die or chip size. As an example, in December 2019, TSMC announced an average yield of 80%, with a peak yield per wafer of GT 90% for their 5nm test chips with a die size of 17.92 mm. The yield went down to 32.0% with an increase in die size to 100 mm 2.40. The fab tests the chips on the wafer with an electronic tester that presses tiny probes against the chip. The machine marks each bad chip with a drop of dye. Currently, electronic dye marking is possible if wafer test data, results, are logged into a central computer database and chips are binned, i.e. sorted into virtual bins, according to predetermined test limits such as maximum operating frequencies /clocks, number of working, fully functional, cores per chip, etc. The resulting binning data can be graphed, or logged, on a wafer map to trace manufacturing defects and mark bad chips. This map can also be used during wafer assembly and packaging. Binning allows chips that would otherwise be rejected to be reused in lower-tier products, as is the case with GPUs and CPUs, increasing device yield, especially since very few chips are fully functional, have all cores functioning correctly. For example, fuses may be used to disconnect parts of chips such as cores, either because they didn't work as intended during binning, or as part of market segmentation, using the same chip for low, mid and high-end tiers. Chips may have spare parts to allow the chip to fully pass testing even if it has several non-working parts. Chips are also tested again after packaging, as the bond wires may be missing, or analog performance may be altered by the package. This is referred to as the final test. Chips may also be imaged using X-rays. Usually, the fab charges for testing time, with prices in the order of cents per second. Testing times vary from a few milliseconds to a couple of seconds, and the test software is optimized for reduced testing time. Multiple chip, multi-site testing is also possible because many testers have the resources to perform most or all of the tests in parallel and on several chips at once. Chips are often designed with testability features such as scan chains or a built-in self-test to speed testing and reduce testing costs. In certain designs that use specialized analog fab processes, wafers are also laser trimmed during testing, in order to achieve tightly distributed resistance values as specified by their design. Good designs try to test and statistically manage corners, extremes of silicon behavior caused by a high operating temperature combined with the extremes of fab processing steps. Most designs cope with at least 64 corners. Device yield. Device yield or die yield is the number of working chips or dies on a wafer, given in percentage since the number of chips on a wafer, die per wafer, DPW, can vary depending on the chip's size and the wafer's diameter. Yield degradation is a reduction in yield, which historically was mainly caused by dust particles. However, since the 1990s, yield degradation is mainly caused by process variation, the process itself and both tools used in chip manufacturing, although dust still remains a problem in many older fabs. Dust particles have an increasing effect on yield as feature sizes are shrunk with newer processes. Automation and the use of mini-environments inside of production equipment, FOUPs and SMIFs have enabled a reduction in defects caused by dust particles. Device yield must be kept high to reduce the selling price of working chips, since working chips have to pay for those chips that failed, and to reduce the cost of wafer processing. Yield can also be affected by the design and operation of the fab. Tight control over contaminants and the production process are necessary to increase yield. Contaminants may be chemical contaminants or be dust particles. Killer defects are those caused by dust particles that cause complete failure of the device, such as a transistor. There are also harmless defects. A particle needs to be 1/5 the size of a feature to cause a killer defect. So if a feature is 100 nm across, a particle only needs to be 20 nm across to cause a killer defect. Electrostatic electricity can also affect yield adversely. Chemical contaminants or impurities include heavy metals such as iron, copper, nickel, zinc, chromium, gold, mercury and silver, alkali metals such as sodium, potassium and lithium, and elements such as aluminum, magnesium, calcium, chlorine, sulfur, carbon, and fluorine. It is important for these elements to not remain in contact with the silicon, as they could reduce yield. Chemical mixtures may be used to remove these elements from the silicon. Different mixtures are effective against different elements. Several models are used to estimate yield. They are Murphy's model, Poisson's model, the binomial model, Moore's model and Seed's model. There is no universal model. A model has to be chosen based on actual yield distribution, the location of defective chips. For example, Murphy's model assumes that yield loss occurs more at the edges of the wafer. Non-working chips are concentrated on the edges of the wafer. Poisson's model assumes that defective dies are spread relatively evenly across the wafer, and Seed's model assumes that defective dies are clustered together. 41. Smaller dies cost less to produce, since more fit on a wafer. And wafers are processed and priced as whole, and can help achieve higher yields since smaller dies have a lower chance of having a defect, due to their lower surface area on the wafer. However, smaller dies require smaller features to achieve the same functions of larger dies or surpass them, and smaller features require reduced process variation and increased purity, reduced contamination, to maintain high yields. Metrology tools are used to inspect wafers during the production process and predict yield, so wafers predicted to have too many defects may be scrapped to save on processing costs. 42. Die preparation. Once tested, a wafer is typically reduced in thickness in a process also known as backlap. 43. Back finish or wafer thinning. 44. Before the wafer is scored and then broken into individual dies, a process known as wafer dicing. Only the good, unmarked chips are packaged.
Yes. The video's ready. I need to get something to drink. I have to wash my fingers. I was eating this candy. Good. I have to update my week lists, or my playlists. Good. So let's finish this. This camcorder is finished charging. I like to finish everything before I go to bed, so I not wake up tomorrow. I have to upload a lot. We have that's from my t-shirts, small, I don't know what you call it. That's from my t-shirt. Let's go to my kitchen. Yes, that's for the garbage. The one there. There. And not going to eat more candy tonight. Let's put it away. The video will split. Yes, let's make lemonade. This is supposed to be a hot weekend. Good. So there's a lot of juice for the weekends. There. That's 8 liters. 2 there. There. Water. We could put some fresh water there. Then I have juice and water for the weekends, Saturday and Sunday. This is 10 liters, so that's enough for Monday, but we have to do something more juice tomorrow. Yes, let's go wash my hands because I was eating this candy. I have to check my front door a final time because I can have strangers. I have strangers around my apartment building because I'm YouTuber. That's teenage boys and young males do that, knocking on doors.